Hi, I am Professor Angela Rasmussen from the Electrical and Computer Engineering Department at the University of Utah. For this example, we are going to look at designing a system that uses op-amps. So we want to do three things. First, we want to calculate this V3 equation, and then we want to see if the V3 is under these conditions. We want to meet these V out. We also need to look at the power to the op-amps, and we can use either a plus or 15 minus volts, and then we also know that we have a 10 volt power supply in the circuit. So we first want to see, okay, if we're going to try to achieve this V3 equation, we need to have two inputs, V1 and V2, and they're going to go into some circuit, and out of that we're going to get V3, which will be the actual equation. So we need something that is going to give us that output. From there it's going to go into another circuit, and depending on the comparison within there, we're going to get either a plus 15 volts out or a minus 15 volts. So we look at the options for this first block. So in order to achieve this, we know we have an inverting circuit. For an inverting op-amp, we have a non-inverting op-amp, but that only has single inputs. We have a voltage follower, which also only has one single input. For the circuits that we're familiar with two inputs, such as this, we have a non-inverting summer, an inverting summer, and a difference, meaning it would have an opposite sign for one of them, such as a subtraction. So since we have these are both adding and they're both positive, we could maybe use a non-inverting summer. So we would want to look at that. For this block, we know we have a circuit that when you have a comparison such as this, then you could achieve the rails of plus 15 or minus 15 volts. So we're going to try and see, is a comparator going to give us an accurate output here? So we're going to first look at the non-inverting summer and see if we can use that for the design. So looking at the circuit cards, we're going to go down to the non-inverting summer. And I'm going to copy those cards up here. So we see from this card that this is the side that's going to show us the equation that we could achieve from here. So this is going to be what we could achieve. Now we can see that yes, we want to achieve this V3 is 3V1 plus 9V2. If that's the case, then our output's going to be V3. This would be our output location. And then that would be the same on the other side of the card. This would be our output location. If we said that V1 was this first input, that would be on this wire, and V2 would be for this VTH2, so we would have V2 on this wire. So we say, can we achieve a G, G1, and G2 values that would achieve 3V1 plus 9V2? We see that G1 and G2 have to be less than 1. That's what this says right here. And that G has to be greater than or equal to 1. So kind of a way we could say is that G, if we sum up the coefficients, that would give us 12. And if we add 12 and we multiply it for G to give 3 over 12 V1, that would give us 3V1. And if we did 9 over 12 V2, that would give us 9V2. So this could be reduced down to 1/4, and this would be down to 3/4. So we say, okay, this all multiplied out. Yes, this would give 3v1 plus 9v2. So then we look at how we would design this is that the G equal to 12. We go back to this card and we see the equation for G. That's RS plus RF over RS. And if we set RS to be 1K, that would give RF as 11K, and we would have 12K over 1K, which would give us a ratio of 12. So that would be our values for RS and RF, which are in this side. And then for G1 is 1/4. And we look at the equation for G1, we're ignoring the RTH values since we don't have any connections before this. And that equation is RB over RA plus RB. And then if we set RB to 1K and RA to 3K, we would achieve that 1/4. For G2, we have 3/4, and our equation is RA over RA plus RB. And we just need to check that this will work. So if we have RA is 3K and RA and RB is 4K, that gives us the 3/4. So these values for RA and RB will work for this design. So this will work as a non-inverting summer and let us achieve this V3 equals to 3v1 plus 9v2. So now we want to look at the comparator. The comparator circuit, remember, has no feedback, and we have the two sides, a plus side and a minus side, and then we're going to have plus 15 volts and a minus 15 for this circuit. So then we need to decide what are going to be on the inputs to this op-amp. So for one of them, we're going to, since we want to compare it against the value of 10, we're going to place 10 volts on one of these terminals, either VN or VP, and the other one would have V3. So we know that we want to have V3 is greater than the 10. We want a plus 15 volts out. That will be achieved when we have the plus side greater than the negative side. So if we have 10 volts on the minus side and we put V3 on this positive side, when V3 is greater than 10, then we would get the plus 15 volts out, which is what we want to achieve. We then check if V3 is less than 10, then we're going to get this negative 15 volts out, which is what we want from this. So that would achieve our end goal. So the output of this is going to be VO. So now I'm going to copy the circuit card, and we're going to redraw that circuit. And this one was where V2 was coming in, and this one was where V1 was coming in. RA was 3K, so this value will be 3K. Our RB was 1K. That goes into the positive side of the op-amp. And the negative side had the RS value to ground, and the RS was 1K. And then it had the RF value that's fed here, and this output was V3, and the RF was 11K. The output V3 then goes into the plus terminal of this one, and then I put the 10 volt comparator or comparison on the negative terminal, and these are hooked to plus 15 volts and minus 15 volts, and the output of that gives me VO. So this is my circuit design for this example, and this concludes that.